So let's explain how TCP works. We know that, actually we go back a little bit, we know TCP, we have a segment. The segment contains the information listed here in the header, plus the data. Some important things included in the header of the TCP segment are the source port and destination port. Port numbers identify applications. Web server uses port number 80. Your web browser may use a random unassigned port number. Those port numbers identify which applications are communicating. Inside the TCP header we include a sequence number and sometimes also, well, there's a field also for an acknowledgement number. The sequence number, when we're sending data, it identifies the data that we're sending, because we may send, if we want to transfer a megabyte between one source application and a destination application, then we'll send that in multiple segments, and we'll use sequence numbers to keep track of the order of that data. And we'll acknowledge that data. When we send data, the receiver will eventually send back a segment which is acknowledging the data that it's received. And include an acknowledgement number. And the same concept that we've covered or we've mentioned early in the semester, if I send sequence number 1, then the receiver will send back an acknowledgement saying, thank you, I've received 1, acknowledgement number 2, saying the next number expected. That still applies for TCP. The acknowledgement number indicates the next sequence number expected, not the last one received, the next one expected. There are some other fields, but importantly there's some flags, and the flags, the ones that we've seen so far, are SYN and ACK. The SYN flag is just 1-bit value. When that flag is set to 1, it means this segment is used for synchronizing the sequence numbers, which is only on startup when we set up the connection. We'll see an example of that in a moment. The ACK flag, when that's set to 1, it means this segment contains an acknowledgement for some data that's been received. So a segment may contain data, and it will have a sequence number for that data. And if the ACK flag is set to 1, then the acknowledgement number also is important, because the segment contains data in one direction and an acknowledgement for data that's been received. So a single segment can have two meanings, or have two purposes: carry the data and also carry an acknowledgement at the same time. This is the concept of piggybacking. In TCP we establish a connection from source to destination, from client to server, before we transfer data. The way that we establish the connection is using this three-way handshake. The client initiates communications by sending a special TCP segment where the SYN flag is set and the sequence number contains some value chosen by A, the source. So it chooses a sequence number that it wants to start with. We don't have to start with 0. We can usually start with a number that has not been used previously. Tells B its initial sequence number. B responds with one TCP segment which has two meanings. The first meaning is that in its acknowledgement for the initial sequence number that B has received. So we acknowledge the first segment by setting the ACK flag to true and including in the acknowledgement number field one more than the initial sequence number received. So if we receive initial sequence number 10, the acknowledgement number will be 11, saying, thank you, I agree that we can use that initial sequence number that you suggested in the previous packet. This segment contains also B's initial sequence number. Because we can transfer data in both directions independently. A can send a lot of data to B, while B is also sending data to A. That data transfer is independent. We use different sequence numbers for each direction. So B chooses an initial sequence number and tells A the value by including it in this TCP segment. Sets the SYN flag to say this contains my initial sequence number and sets the value in the sequence number. And when A receives that, A knows two things. A knows the value of the initial sequence number chosen by B, and A knows that B has accepted A's proposed value from the acknowledgement. A proposes a value, B accepts that and acknowledges it, and B proposes its own value for the other direction. And the final step, if everything's okay, is A sends back one more TCP segment. It's an acknowledgement for the initial sequence number that B has proposed. And again, we set the acknowledgement number to be the value proposed plus 1 and set the ACK flag to be true. So that's the basic procedure for a successful connection setup. It can be unsuccessful. B could say, no, I don't want it to connect. So there are some other messages that are exchanged in that case. We just focus on the successful case. There's one extension of this. This is the connection setup. After this, we can transfer data. An extension of this is this last segment, the third one here, and only this one. It could also contain data. SYN, SYN-ACK, ACK, or optionally we could do SYN, SYN-ACK, and with this ACK also include the first piece of data that A sends to B. So include some data in this segment and set the sequence number to be the appropriate value. So we can optionally include data in the last segment. We don't have to, but it saves the number of segments we send if we can. When we want to, so we establish a connection, transfer data, and then when we finish transferring data, either A or B can initiate closing the connection. We won't go through the steps. We use the fin flag to say finish, and there are some other options available too. So this is to say we've got no more data to transfer. In TCP, we can have what's called a half-open connection. A can tell B, I've finished transferring data, I've got no more data to send. So A closes its side of the connection, so A will no longer send data. But after that, B can keep sending data to A until B closes the connection from its side. And once they're both closed, then the connection is finished, is closed. There are different ways to close a connection using a reset flag. If something goes wrong, you can close the connection without waiting for an acknowledgement. So let's look at the data transfer part of it. That's closing. We looked at opening the connection. Now, what about when we transfer data? TCP uses a sliding window mechanism. Same concept we've seen in other topics, where we can send multiple segments or multiple bytes before we have to wait for an ACK. TCP uses different algorithms for error control, so that is retransmission schemes, flow control to making sure that the source doesn't overflow the sender, and congestion control, making sure the source doesn't overflow the routers along the path. We will see an example of the error control. The flow and congestion control we will not cover. Flow control is similar to what we've seen in previous topics. Congestion control is much more complex. Some details of these algorithms depend upon the implementation. Your implementation in a Mac operating system may be different from a Windows operating system. So they'll be able to communicate with each other, but the fine details of how they work may differ. For example, if you send data segments, sometimes you can send one ACK for every data segment received, or you could send one ACK for every 2 data segments received, or one ACK every 1 second. So there are different options for when to send an acknowledgement in response to data. That's up to an implementation. It impacts upon performance of TCP. Let's look at an example of how TCP uses sequence numbers. Importantly, TCP is a stream-oriented data transfer service. What that means is when the application generates data as messages, TCP doesn't distinguish between multiple messages. It just treats the data as a stream of bytes. It doesn't care what those bytes are. It doesn't care whether one group of bytes correspond to one message and another group to a second message. It treats them all as a stream of bytes. As a result, TCP may not send messages as separate segments. It may combine them into one segment, or it may split a message into multiple segments. And there are different ways that implementations will deal with that. We'll see some examples. First, let's look at how TCP treats segments and sequence numbers. In the connection setup, we agree upon initial sequence numbers. For an example, or this example, let's say, and we're focusing on data going from A to B. Let's say A chose the initial sequence number, in this example, of 300. So that was agreed upon in the connection setup phase. B also chose an initial sequence number, but for this example, we're just going to focus on going from A to B. And in this case, A has 10,000 bytes of data to send to B. I'll draw a diagram that shows the steps that we go through. This diagram is in fact on one of the later slides. It'll be slightly different. I'm going to draw this on the board. It's going to be slightly different notation, but we'll see the correspondence. At the start, after setting up a connection, I'll draw that. This is our connection setup phase. Those three messages, the TCP Three-Way Handshake, send a SYN, SYN-ACK, ACK. And after that's completed, we can transfer data. So at this time, A has 10,000 bytes of data to send to B. The application at A wants to send 10,000 bytes of data to an application at B using TCP. TCP uses sequence numbers to count bytes. And the way that it works is that if we have that, look at that 10,000 bytes of data that the application wants to send, the application delivers that 10,000 bytes to TCP at the sender side, and we can number every byte starting from our sequence number 301 up to 10,300. That is, this is our 10,000 bytes if we draw it, byte 1 up to byte 10,000. Our initial sequence number chosen is 300, which really means that the first byte of data we send is going to be 301. Because remember how it works is SYN, initial sequence number 300, the ACK will come back saying, thank you, I now expect 301. So if the initial sequence number is 300, the first sequence number that's going to be sent with data is going to be 301. So we can think the first byte has sequence number 301, the second byte 302, and the last byte of these 10,000 would be 10,300. If you number all of the bytes, we can think each has a sequence number. TCP takes the data that came from the application and, according to its algorithms for flow control, error control, congestion control, to optimize performance, it decides how to send that data as segments. It doesn't have to send this as all one segment, as one packet across the network. It can break it into multiple segments. And it can determine the size of those segments, depending on different criteria. In this example, it's not a very realistic example, but it illustrates the different options that TCP has. In this example, the TCP is going to decide, I've got 10,000 bytes to send, I'm going to send it as 4 different segments. The first segment going to contain 1,000 bytes, the second segment 1,000, the third 4,000, and then 4,000. Why did it do that? It just did that for the example. The exact way to split the data into segments depends upon a number of different algorithms. It's very hard to predict what it will do unless we know the exact conditions of how the computers are communicating and when the data arrives. So just as in this example, it decides to split into 4 different blocks. In another example, it may decide to split into 2 blocks of 5,000 and 5,000. So we have 4 blocks of data now. Continuing on this diagram, so that's what we have at the top. Now TCP creates the segments, and a TCP segment contains data plus a header. So we take those 4 blocks of data and create 4 TCP segments shown here. Header, H means header, and the data, the first 1,000 bytes, a header with the second 1,000, a header with the 4,000 bytes, and a header with the last 4,000 bytes. So we're going to have 4 TCP segments to send in this case. The header contains all those fields that we've seen in one of the previous slides. The source and destination port will be the same in all 4 segments. But let's focus on the sequence number field in each header. The sequence number field in the header indicates the sequence number for the first byte of data in that segment. Remember, we numbered the bytes from 301 up to 10,300. So, the first TCP segment goes from 301. Let's be a bit more detailed here. So if we take this first piece of data, then what sequence numbers does it contain? 301, 302, 303. It contains 1,000 bytes. And the last sequence number in this first segment will be 1,300. This segment contains 1,000 bytes. If we number those bytes, the first number is 301, then 302. If you keep counting for 1,000 bytes, you'll get up to 1,300. 1,000 bytes in there. And of course, we include the header. That is our entire TCP segment. And the value of the sequence number field in the header is the value of the sequence number of the first byte of this data. That is what we've drawn here. The first segment contains sequence numbers from 301 up to 1,300. The second segment also contains 1,000 bytes. If this was 1,300, then the next byte must be 1,301. And it will go up to 2,300. Therefore, when we attach the header, the sequence number, the value of the sequence number is the value of the sequence number for the first byte in that segment, which is 1,301. And we do that for the last 2 segments. So this one will start at 2,301. This started at 1,301, and this has 4,000 bytes, so the next one will start at 6,301. And we get the segments as shown here, where it shows the value of the sequence number that's included in the header. It's the sequence number of the first byte in here. So this is illustrating that although the application delivered 10,000 bytes to TCP, TCP doesn't care that that 10,000 bytes came together. It just treats it as a sequence of bytes, a stream of bytes. And it will use its own algorithms to decide how to send that 10,000 bytes across the network. In this example, it decided to send it in 4 segments of 2 different sizes. In a different example, it may split it up in a different way. And it simply gives the sequence number field in the header the value of the first byte contained in that segment. And we send these 4 segments across the internet. That is, we take the first TCP segment, put it inside an IP datagram, so attach an IP header, and transmit that across the internet. It will get to the destination will receive and process, and will receive the first 1,000 bytes of data. In the meantime, the source has created the second segment, puts it into an IP datagram and sends that across the internet. So it would send 4 IP datagrams across the internet. The destination hopefully will eventually receive those 4 datagrams, maybe in order, maybe not, and has then received the 10,000 bytes of data. We could draw that like this. That is, this is the first segment. To indicate that it contains data, that's a TCP segment containing data, I'll just write the word data. And the sequence number for this data was 301. This is just to show that we have a TCP segment sent from A to B. It contains some data. To make note, just so we remember, it has 1,000 bytes of data, and the sequence number is 301. And we can send the second segment, and the third and the fourth. And eventually some acknowledgements will come back. Let's check. In this example, I've illustrated sending 1 segment at a time, receiving an acknowledgement. Send the first segment, receive an ACK. Note the acknowledgement number. When B receives the first segment, B has received data with sequence number from 301 up to 1,300. So at this point in time, after receiving the first segment, B has received all the data up until 1,300, and therefore sends an ACK with ACK number 1,301. I've received everything up until 1,300. I'm now expecting 1,301. That's what this acknowledgement means. The second data segment is sent, this one, containing sequence number 1,301 up until 2,300. When B receives that, if we keep track, after receiving the first segment, B has received sequence numbers 301 up to 1,300 and sends a corresponding ACK. After receiving the second segment, it's received sequence numbers 1,301 up to 2,301. It's received everything in order. The initial sequence number it expected, or we start from, was 300. So in fact it expects to receive 301 and keep receiving the data in order. And it's important that it's in order. If something arrives out of order, then we may have to do something about it. We'll see that with error control. So we send back an ACK here saying, I now expect to receive 2301. That's the next sequence number in order. When we receive the third segment, it contains bytes 2301 up to 6300. Successfully received, send back an ACK saying I now expect 6301. When we receive the fourth segment here, it contains bytes 6301 up to 10,300. And hence we get the final ACK saying I now expect 10,301. And, all right, I started to draw here, but it's the same diagram. I won't draw it in detail. Data ACK, data ACK, data ACK, data ACK. That's those four segments, or four exchanges. That was to transfer the 10,000 bytes of data that the application at computer A wanted to send to the application at computer B. In this example, we sent it as 4 segments. Let's say the application sometime later wants to send some more data. The first 10,000 bytes was triggered by the user on the application opening a file to upload and pressing send. It was sent as 4 segments. 5 minutes or 1 minute later, the user has another file to send and presses send. This second file is 20,000 bytes. If the connection is still open, we continue the transfer using these sequence numbers. So if we have 20,000 bytes, you can think TCP would break that into segments starting from 10,301 up until whatever. If we broke it into segments of 2,000 bytes, it'd go up to 12,300 and so on. That is, the next piece of data that the application wants to send continues on from the previous set. So the next segment here would be a data segment containing sequence number. What sequence number? What sequence number? 10301. 10301. Good. The acknowledgement here says we expect 10301, so the next data is going to be 10301. He's very smart, this guy. And the next one, see if he's in luck. Next one. Did you just guess that one, or?
No, from...
Okay. And the next one, that one was to contain 2,000 bytes. The next one will be?
123.
12301. Good. If TCP decided to break it into chunks of 2,000 bytes this time, then it would be 10,301 up to 12,300, and then 12,301 up to 14,300, and so on. So that 20,000 bytes of data that we want to send would be sent as multiple segments across the internet. And if we have more data to send, we'll keep using those increasing sequence numbers. So that's how sequence numbers are used in TCP. Importantly, that's different than what we've seen in previous topics. The sequence numbers here count bytes. In previous topics, sequence numbers counted segments or frames. That is, frame 1, frame 2, frame 3. That's not the case with TCP. Here, the sequence number indicates the byte. So the next sequence number, it's not 1, 2, 3. It depends upon the number of bytes included in the data. Other than that, it's the same what we've seen in the different flow and error control mechanisms. So that's TCP data transfer. Of course, it doesn't have to happen like this. That is, data, ACK, data, ACK, data, ACK. TCP uses a sliding window mechanism. It could have been the source sending the data one after the other. With a sliding window, we're allowed to send multiple segments before we have to wait for an acknowledgement. These are the ACKs coming back. So it could have been like this in a different case. Or in this case, we sent 4 segments. The amount that is allowed to be sent depends upon the flow control and congestion control scheme, the window size. And then we sent an ACK for every segment received. Alternatively, it could have been like this: send 4 segments. So this is these 4 segments. And the receiver may make a decision, let's not send an ACK for every segment received, let's wait some time, okay, and perhaps send an ACK for every 2 segments received. Do not send an ACK after the first segment, send after the second one, and so on. Or some other mechanism, that is, wait for some period of time, 5 milliseconds. If you have not received more data, send an ACK. If you receive more data, wait until you have nothing received, then send an ACK. The more ACKs you send, the more overhead there is. So it makes sense sometimes to not immediately send an ACK, but to wait and send an ACK later. In this case, the acknowledgement and sequence numbers would be the same as here. Data 301, 1301, and so on, and the ACKs would be 1301, 2301, 6301, 10301. So it would be the same numbers as what we got here. In this case, it would be slightly different. These are sequence numbers. They're the same. We've got 2301 and 6301. The sequence numbers of the data do not change. But in this case, if we send an ACK after the second segment is received, what's the acknowledgement number? What's the acknowledgement number if we send an ACK after the second segment received? Think about the data that's been received, the sequence numbers that have been received if we receive the first 2 segments. We receive the first 2 segments. So we send an ACK saying, what's the next sequence number expected? 2301. The first 2 segments, 301 up to 1300, segment 1, and the second segment. So after receiving the first 2 segments, B has received all the data up until 2300. So it sends one ACK with the ACK number equals 2301, saying I now expect to receive 2301. And the last ACK here would have an ACK number 10301. So that's a way that one ACK can acknowledge 2 segments received. It's essentially acknowledging the reception of these 2 segments. So the ACK numbers acknowledge the bytes that have been successfully received up until now. And we can have variations of those schemes. what do we do if something goes wrong? This is just what we've just went through illustrated if all the data was delivered successfully. We'll look at what happens if some of the data doesn't get to the destination. How do we deal with that data loss? That is, how does TCP Error Control work? And once we go through this, we'll be finished with TCP. TCP uses a selective retransmission style ARQ scheme. So we've covered this scheme before, where we can send a window size of frames. If one is lost, we'll have to retransmit that one. It's not go back n, where we have to retransmit all n frames. We only need to retransmit that one lost frame. ACK numbers indicate the next in-order sequence number expected. As we saw here, the acknowledgement number, we expect the next value 2301. That's what we've seen before. With a selective retransmission scheme, because we ask only a single segment to be retransmitted, the receiver must have some buffers to store segments received out of order. So add some complexity or some memory requirements on the receiver. And as we've seen in normal ARQ schemes, if we don't receive an ACK within some timeout period, retransmit. So we send our data, we wait for an ACK. If we don't receive an ACK, we're going to retransmit that data. So this is concepts we've seen before. ACK numbers, or the concept of cumulative ACKs can be used. This is a cumulative ACK. It acknowledges multiple segments received. We accumulated the sequence numbers received and send a single ACK. Let's go through the basic form for error control or retransmission, and then we'll see an optimized form of retransmission. What this diagram shows, we'll go through in some detail, but we have a host wanting to send data to host A to send data to host B. In this example, it's got 6 segments to send. Just to keep it simple, we're going to start with an initial sequence number 0. Therefore, the first sequence number will be 1. Every segment contains 1,000 bytes, just to keep it simple in the example. 6 segments, so 6,000 bytes to send from A to B. And B, whenever it receives a segment, is going to send an ACK for each segment received. So let's go through the steps of what happens. A sends the first segment, transmits, and immediately A starts sending the second segment. And then the third, and the fourth, and the fifth, and the sixth. Because the window size of A, in this case, allows it to send 6 segments without having to wait for an ACK, just in this example. If there was no data loss, then all 6 segments will be received and we'd receive 6 ACKs back and everything would be done. We could move on to sending more data. But in this case, we have one of these segments is lost. There's an error in the network, in the internet somewhere. The first 2 segments get delivered to B, but the third segment is lost. It doesn't get to the destination. How does TCP deal with that? Well, after B receives the first segment, it sends back an ACK. Let's keep track of our numbers. Let's look at what B has received. After receiving the first segment had a sequence number 1 and it contains 1,000 bytes. Therefore, that B has received sequence number 1 up to 1,000. That was successful. We're assuming that the initial sequence number that A chose is 0. So in the connection setup, A chooses initial sequence number 0, therefore the first data segment is going to have sequence number 1. When B receives the first data segment, it's received these bytes of the data. That was fine. Then B receives the second data segment, which contains sequence numbers 1001 up to 2000. I skipped. B sent an ACK after the first segment. We received up to 1000, sent an ACK saying I now expect 1001. Before, or in the meantime, it receives the second segment and therefore sends an ACK for that second segment. So that's normal. From B's perspective, after sending this second ACK, ACK 2001, it's waiting. This segment was transmitted by A, but it's not going to be received by B. It's lost somewhere in the internet. So B is waiting, and eventually B receives this segment. It contains sequence numbers 3001, the fourth segment, 3001, containing 1000 bytes, so it goes up to 4000. And it's at this point in time that B recognises something's gone wrong. Or potentially some data may be lost. Because B expects to receive the data in order. We've transmit the data in order, we should receive the data in order of sequence numbers. We've received from sequence number 1 up to 2000 and 3001 up to 4000. Where is 2001? Well, B simply sends an acknowledgement back, but B always acknowledges the next in order sequence number expected. It's still expecting 2001. So B sends back an ACK saying, I expect to receive sequence number 2001. It stores this data in memory, in a buffer, because it will use it later. But it's still expecting to receive the data that's missing here. The fifth segment transmitted is eventually received by B, and that contains sequence numbers 4001 up to 5000. B is still expecting 2001, so sends back an ACK saying, I want to receive sequence number 2001, because I want to receive in order. And the last segment that was transmitted from 5001 up to 6000 is received. These three are buffered by B, but it's still expecting to receive 2001. So it sent these three ACKs, all with acknowledgement number 2001. After that, B's waiting to receive more data, especially 2001. Come back to A, what happens? A transmits its 6 frames. It's expecting to receive ACKs, indicating that those frames, or those segments have been successfully received. It receives the first ACK saying B has received up until 1001. That acknowledges the first segment sent, because A knows the first segment was from 1 up to 1000. If B is expecting 1001, that means the first segment has been successful. Then A receives the second ACK saying B has received up until 2001, meaning the second segment has been successful. Then it receives sometime later an ACK saying B is still expecting to receive 2001. So from A's perspective, we don't need to write it. From A's perspective, bytes 1 up to 2000 have been successfully acknowledged at this point. Then it receives an ACK saying I'm expecting to receive 2001, so still bytes 1 up to 2000 have been acknowledged, nothing further, and receives those same ACK numbers. So from A's perspective, bytes 1 to 2000 have been successful. After it transmits each segment, A starts a timer. It expects to receive an acknowledgement for that segment within some timeout period. It's received acknowledgements for the first two segments, but the third one, containing numbers 2001 onwards, it hasn't received an ACK for. And when the timeout expires, that triggers A to retransmit that segment. So we start the timer at each segment. This timer will be cancelled because we receive an ACK. The timer for this segment will be cancelled because we receive an ACK. The timer for this segment will eventually time out, that is, will reach the maximum value. That triggers A to say, okay, the third segment containing 2001 must have been lost. Therefore, I'll retransmit that segment. It retransmits the segment. In this case, it's not lost, it gets delivered to the destination. So when B receives this segment successfully, it contains bytes 2001 up to 3000. And now from B's perspective, it's received bytes 1 up to 6000. It's received everything, or all 6000 bytes in order now. Before this, it had received the first 2000 and the last 3000. These were stored in memory, in a buffer. Once it receives this missing segment, it's received everything in order. And so it sends back an ACK saying, I now expect to receive 6001, the next in order number. A, when it receives this ACK, knows that all of the data that it has sent has been successfully delivered. If A receives an ACK with ACK number 6001, it means B has received data up until 6000, which means all 6 segments. So now we've finished our data transfer. We could move on to sending more data. A has sent the 6 segments. It realised because of the timeout one of them was lost. It didn't receive an ACK within the time allowed. Therefore, it retransmitted that one segment. So this is selective retransmit. And eventually gets an ACK. And that ACK, with the ACK number 6001, indicates to A that everything from 1 up to 6000 has been successfully received, and can move on to sending more data if it has it. That's the basic retransmission scheme used by TCP. There can be variations, or it can be different scenarios can arise in terms of the number of ACKs that come back. It doesn't have to be one for every segment. It could be one for every 2 segments, for example, but the same concept. Have a timer for each segment you send. If you don't receive an ACK within the timeout period, retransmit. Destination, when it sends an ACK, the ACK number is the next in order sequence number expected. Even if we receive things out of order later, that is from 3001 up to 6000, we still were expecting 2001. Once we receive all of the data and we've got bytes 1 up to 6000 in order, we can send ACK 6001. What's the problem with this? The problem with any retransmission scheme when we wait for a timeout is that we may have to wait for a long time. From A's perspective, it sends some data, transmits, and then it's waiting. It's waiting for an ACK, waiting for a long time. All that time spent waiting leads to inefficiencies in using the network. The longer the time we spend waiting, the less efficient the data transfer is. How long should the timeout interval be? How long should we wait before we retransmit? It needs to be long enough to allow B to send back an ACK. But in the internet, how long does it take to get a data segment from my computer to some other computer? How long does it take to you to communicate with some other computer in the internet? On your phone or your laptop, how long does it take to send a message to another computer? 2 seconds. The answer is going to depend upon which other computer you're communicating with. If you're communicating between my laptop and this computer, they're both internet communications, then the answer may be a matter of microseconds, milliseconds. If you're communicating with a computer on the other side of the world, it may be hundreds of milliseconds, even longer. So in fact, we cannot predict what the timeout interval should be, and therefore we usually make it quite large to cater for all different cases. The larger it is, the less efficient it is. So this may have a problem because when we lose data, we have to wait a long time before we retransmit. So one way to improve upon that is some optimization called fast retransmit. The previous one was a basic retransmission scheme. This is the fast retransmit scheme. Everything's the same. In this example, send 6 segments. The third segment's lost. B behaves in the same manner. Sends the ACK. ACK 1001. ACK, I'm expecting 2001. Doesn't receive 2001 but receives 3001. ACK, I'm expecting 2001. Again 2001. Again 2001. That's the same as the previous case. From A's perspective, after sending each segment, it starts the timer. That's the same as before. A has transmitted 6 segments. It receives ACK 1001. Okay. ACK 2001. That's okay. And then it receives ACK 2001 again. That indicates maybe something's not okay. I'd expect to receive ACK 3001 because I know I've sent data from 2001 up to 3000. I'm expecting ACK 3001, but I just received ACK 2001, a duplicate of the previous ACK. It's the same value here. And then I receive another ACK 2001, and then a third duplicate of the original 2001. And at this point I realise, or I make an assumption, I know I have sent sequence number 2001 to 3000, but it looks like B has not received it because B is keep telling me, please send 2001, 2001, 2001. And the scheme in TCP fast retransmit is if you receive 3 ACKs with duplicate ACK numbers to the previous one, then retransmit immediately. Or in other words, if you receive 4 ACKs with the same number, retransmit. That is, send this segment again. Once that's received, then we get the final ACK. Everything's okay. So the difference between the two is, where's our slide, is the amount of time it takes to retransmit. In the basic scheme, we have to wait until the timeout expires and then retransmit. If the timeout interval is very long, we have to wait a long time. In fast retransmit, if we still have a timer, but if we receive this special instance of 4 ACKs with the same ACK number, or it's referred to as 3 duplicate ACKs, then we retransmit the frame that is believed to be lost. That is, we retransmit before the timer expires. And that saves us some time and improves the efficiency of our data transfer. So really, fast retransmit can improve the performance of the data transfer in the presence of lost segments. If we don't receive 3 duplicate ACKs, we still have the timer. Maybe the timer will expire down here and we'd retransmit. But in this scenario, we receive the 3 duplicate ACKs, retransmit, get the final ACK, and then we're success. We've transferred all of our data. So this is an optimization for TCP performance. So in fact, both of the schemes are used today. If a timeout expires, retransmit, or if you receive 3 duplicate ACKs, retransmit, whichever one happens first. It depends upon the network and the performance of the network as to which one will happen first. So that's 2 mechanisms used in TCP error control. There are some further optimizations that have been applied. For example, if we lose multiple segments, not just one, it becomes more complex. But they are the only mechanisms we're going to focus on for this course. We retransmit if a timeout expires or if we receive 3 duplicate ACKs. Any questions on how TCP error control works? That's our last part of TCP. You'll see some previous exam questions that cover what's the difference between basic and fast retransmission. What's the advantage of fast retransmit? Even some past exam questions calculate the time it takes to do all this. Transmission time plus propagation time and so on. Or what happens if you transmit 7 frames and the 5th frame is lost? Then show the ACKs that come back. They are the types of questions you'll see in exams. With TCP, there's also a mechanism for flow control. The aim is to prevent the sender from overflowing the receiver. Use the advertised window field, so it uses a windowing mechanism. Similar to some of the mechanisms we've seen with flow control already, but we're not going to go through it. There's some variations upon what we've seen. It gets a little bit more complex. And even more complex is congestion control. If you send too fast, the routers in the internet may overflow. Therefore, TCP has a mechanism to slow down if it detects such congestion. But the algorithms for that becomes quite complex. Some of you will cover it next semester in internet technologies and applications, if you choose that option. That's it for TCP. But not for today. We still have 15 minutes left. The earlier we finish our next topic, the earlier we'll finish tomorrow. Quiz tomorrow, not today. Let's just get started on the last topic.
How many duplicate ACK that we can receive before we transmit? 3 or
Yep.
other number?
So the fast retransmit scheme is defined as if you receive 3 duplicate ACKs, then you can retransmit. And it's always 3 duplicate ACKs, which in other words means 4 ACKs with the same number. If I receive ACK 2001 and then ACK 2001 3 more times, that triggers me to retransmit the frame with sequence number 2001. So that's the definition of the fast retransmit. 3 duplicate ACKs. It doesn't change from that.
Does it have to be exactly 3?
Yes. It's set to 3 in TCP fast retransmit. The idea is that, to make sure, that is, 1 duplicate ACK may mean that possibly the segment was lost, or maybe it's just been delayed. We don't know whether it's lost or the segment was delayed and the ACK is coming sometime later. 2 means we're a little bit more confident that it's been lost. 3, we say, okay, we're very confident that that segment has been lost. Again, it still may not have been lost, it may be just delayed, but there's a high chance that if we receive 3 ACKs or 3 duplicate ACKs, 4 ACKs with the same number, then it's most likely that that segment was lost. That's why we retransmit. So in TCP it's fixed at 3 duplicate ACKs or 4 of the same number. We have time for more questions on TCP. Sorry?
Why does this sequence come from?
This is what B was keeping track of what was received. B, we'll show the slide again. B, just to indicate what B had received in terms of the sequence numbers. The data that's sent, 6,000 bytes, we always treat each byte with a separate sequence number. We receive the first 1,000 bytes, the second 1,000 bytes. Previously we didn't receive the third 1,000 because that was lost. We received these bytes, and these bytes, and then we retransmitted the one that was lost. So this is showing what B has received. And we need to receive data in order. That's important. This was a different example that we used when we drew data previously. But you see it's all in order. In this example, I divided the data into 1,000 byte segments. In different examples, it can be a different number. I could say it's 2,000 bytes. So I would tell you in an exam or a quiz how large the segments would be. We cannot predict what it would be without further knowledge of flow, congestion control. So just 2 different examples with different size segments. This one 1,000 and 4,000, this one just 1,000. Your quiz tomorrow covers IP addresses, but there's one question on TCP. Not a complex question. One question on TCP about either connection establishment or data transfer or both. Not about retransmission. The quiz tomorrow only. Let's just get started on applications so we can finish this topic. Last topic, we've reached the top of our 5-layer stack. We just covered transport protocol. At the top are the protocols that support our applications, and then many different types of internet applications. You use them every day. You mainly use web browsing, but there are many other type of applications that we can use across the internet. We'll just look at one simple example, web browsing. But I think now we'll just introduce what we mean by internet applications and maybe say a little bit about DNS. So what's an internet application? A software application that uses communications to support its intended purpose for communications between different instances of the application or different clients and servers for that application to support the end user behavior. An internet application, we can think of having a user interface, some application logic, that is the functionality that the application needs to operate. An email application needs something for you to compose and save emails and to look up address books and so on. That's the logic of the application. And importantly, the communications. An email application needs some way to send an email from your application to some other application, a server, for example. We're focusing on the communications part of it. At the communications part of your application, we use some application layer protocol. And there are many different types of internet applications and many different application layer protocols. Some of them are listed here. Instant messaging. You use MSN, the MSN chat, then that's an instant messaging application that uses a messaging protocol, MSNP. If you use Skype or some other voice over IP application, some audio or video communications, conversation, then you may be using protocols like RTP and SIP. So the different protocols to support voice and video conversations. Web browsing, database access, custom applications that are built for businesses in factories, in banks and so on, may have their own communication protocol for their application. Next semester in your lab, you'll write your own simple protocol for your own client-server application. Most of the internet applications use this client-server model. A client contacts the server and then they communicate. And most of them are implemented as software processes at the user level. That's something that you can run and install on your computer without administrator access to that computer. The application layer protocols make use of the transport layer. That is, they use either TCP or perhaps UDP to deliver their data across the internet. There's a programming interface, an API, that allows an application to call the transport protocol, referred to as the sockets interface. And it's used in different operating systems, different programming languages to allow you to write a Java program that will communicate with a C++ program on a different computer by using some common interface. Again, you'll see that next semester. We just want a very quick look at explanation of what do we mean by naming in DNS. And then we'll look at one example application and protocol, HTTP. For most of these applications to work, we need to have human readable names for the end user devices and for the resources we want to access. Let's just introduce what we mean by domain names and the domain name system. We know already that IP addresses identify interfaces. So each computer in the internet has an IP address for that interface. So we use them, the IP addresses, to indicate who is communicating with who. But those IP addresses are used by the computers and used in the packet headers. Domain names are user-friendly ways to identify computers. Rather than remembering an IP address, we may use a domain name. I think you know about the structure of domain names. You use them all every day. There's some hierarchical structure based on different top-level domains and country-level domains. So we have domain names, and more generally we can locate a resource or a file on a particular computer. And we use uniform resource locators or uniform resource identifiers to do that. So some format to identify a particular resource in the internet. And you know the basic structure of the URLs because, again, you use them every day. We identify usually the application protocol that's being used, the scheme that's being used to access a resource. You'll see something like HTTP://. HTTP identifies the application protocol being used to access a resource. We may identify the user to access a particular host on the internet. We'll see an example of that. We identify the device that we want to access. We can specify either the IP address of that device or the domain name. So when you type in an address in your web browser, you type in maybe www.facebook.com. In fact, that's a URL. Maybe the web browser has automatically added the HTTP:// the scheme at the start. You typed in a domain name. You could have typed in an IP address. Both the domain name and the IP address identify the computer you want to communicate with. We can identify the port of the server that we want to communicate with, the destination application. If we don't give it, then normally your application chooses a default port number. And then we usually have a path for the resource that we want to access, some slash followed by some directories and a file name. And there are so many other options and exceptions to these general format of URLs. You've seen them, especially web browsing. We have the scheme, the host that we want to access, and then some path and some file that we want to access. Some directory followed by some file name. Sometimes we can specify an IP address instead of domain name, and we can specify the port number as well. If we don't specify it, then the application will choose a default value. Similar with email, we can have a URL, remote login, and different applications can have URLs to identify resources on the internet. There are many different variations of this. I want to connect to another computer using secure shell. I can specify my username and the computer I want to connect to. I can even specify my password in the URL. So we're not going through the exact structure of them. We just want to say that, all right, we have URLs to identify resources, domain names to identify hosts in the internet. Some way we need to map a domain name to an IP address. Our transport protocols and below, transport and our internet protocol uses IP addresses. We must use IP addresses. But us humans may enter in a domain name. The domain name system, DNS, specifies the format and structure of domain names, this hierarchy of domain names, .com, .net, .th, and so on, and how to map a domain name to an IP address. So DNS, what it does for us, when I type in www.facebook.com as the address on my web browser, DNS goes to work and finds the IP address for the Facebook server, that mapping. And that's the basics of naming and DNS. We'll go through a simple example tomorrow, but that's the main thing that you need to know, that we have domain names, we have as user-friendly names for devices, we have URLs to identify resources, and DNS maps those user-friendly domain names into computer-friendly IP addresses. There are some details of how that mapping works. We'll give a simple example tomorrow, and more importantly, go through an example of how HTTP works. A very simple example for web browsing. And that will finish us for the course after our quiz tomorrow.